There is a problem at the very heart of the artificial intelligence revolution, and almost nobody in the mainstream media is explaining it clearly. It is not about the models. It is not about the chips. It is not even about the money. It is about something far more fundamental: power, electricity, the basic physical infrastructure that a civilization runs on. And right now, in the middle of the most ambitious technological build-out in human history, that infrastructure is failing to keep up in ways that are reshaping the future of AI and raising a question that nobody saw coming. What happens when the companies building the future cannot find enough electricity to power it? Let's understand the scale of what's being attempted. Google, Amazon, Meta, and Microsoft have committed to spending more than $650 billion in 2026 alone, just to expand AI capacity. $650 billion in a single year. That is more than the entire GDP of most countries on Earth, being poured into data centers in 12 months. Each one of these hyperscale facilities, the massive buildings full of servers and cooling systems that run the AI models you use every day, requires between 300 and 500 megawatts of power to operate. That is equivalent to the electricity consumption of an entire mid-sized city, running continuously, every hour, every day, for years. And here is where the story gets interesting. So what is actually causing this? The answer is a component that most people have never thought about in their lives: transformers. Not the movie, the electrical kind. High-voltage transformers are the devices that step electricity up or down as it moves from power plants through transmission lines and eventually into buildings. Every data center needs them. They are not optional. Without them, the electricity sitting in the grid cannot reach the servers. Before 2020, the lead time to order a high-power transformer was 24 to 30 months. Already a long wait for a sector that builds in 12 to 18-month cycles. Today, the lead time is 5 years. 5 years to get a transformer. For a data center that is supposed to be operational in 18 months. And transformers are not the only bottleneck. The grid connection itself, the actual physical hookup that ties a new data center to the electrical network, can take longer still. In Northern Virginia, home to the world's largest concentration of hyperscale data centers, new facilities can face a 14-year wait for a grid connection. 14 years for a connection to a grid that already exists. As of April 2026, approximately half of all planned U.S. data center builds this year are projected to be delayed or canceled. Not because of a shortage of capital, not because of a lack of demand, but because the electrical grid cannot support them. And the problem is not just delays. The United States needs to build approximately 5,000 miles of new high-voltage transmission lines every year just to keep pace with rising electricity demand. In 2024, it completed 888 miles, less than 1/5 of what is required. That gap between the grid the AI industry needs and the grid that actually exists is not a technical problem waiting to be solved by a clever startup. It is a physical infrastructure deficit that took decades to accumulate and will take decades to reverse. Now here is where the story takes a turn that genuinely surprised me when I first looked into it. The companies spending $650 billion on data centers have looked at this problem and reached a conclusion that would have seemed impossible 10 years ago. They are building their own power plants. Not solar farms, not wind turbines, nuclear reactors. Let that land for a second. Microsoft has signed a 20-year, $16 billion deal to restart 3 Mile Island, the site of America's worst nuclear accident in 1979, renamed the Crane Clean Energy Center to power its AI data centers exclusively. Nearly 50 years after a partial meltdown made that name synonymous with nuclear disaster, it is being restarted for artificial intelligence. Amazon has committed over $20 billion to convert the Susquehanna nuclear site into a nuclear-powered AI campus. The facility is expected to consume as much electricity as 900,000 homes and require millions of gallons of cooling water daily from the Susquehanna River. Google has ordered 500 megawatts of small modular reactors from Kairos Power, the first ever corporate purchase of an SMR fleet in the United States. Meta has issued requests for proposals seeking between 1 and 4 gigawatts of new nuclear generation. In total, the major tech companies have signed or announced nuclear deals for nearly 10 gigawatts of capacity, enough to power roughly 7 million homes. They are not just buying electricity anymore. They are financing the construction of power plants directly. And in doing so, they may be succeeding where governments and utility companies failed for 40 years, making nuclear power commercially viable to build again. But even nuclear is not a fast enough solution. Microsoft's 3 Mile Island restart will not deliver power until 2027 at the earliest. Small modular reactors, the next generation of nuclear technology designed to be cheaper and faster to build, are still years away from commercial deployment at scale. In the meantime, the gap is being filled by natural gas. Diesel generators. Emergency power measures that run directly against the sustainability pledges these same companies made to their shareholders and the public not long ago. Google pledged to run on carbon-free energy by 2030. Its actual carbon emissions increased 48% between 2019 and 2024, driven almost entirely by data center energy demands. Microsoft committed to being carbon negative by 2030. Its emissions rose 29% over the same period. This is not simple hypocrisy. It is the collision of two enormous forces, the urgency of the AI race and the physical reality of energy infrastructure, producing outcomes that nobody intended and nobody fully planned for. And then, at the start of 2025, something happened that added an entirely new dimension to this story. A Chinese AI startup called DeepSeek released a model that performed competitively with the best American systems, at a fraction of the computational cost. Meta's Llama 3.1 cost over $60 million in compute to train, using more than 16,000 high-end NVIDIA chips. DeepSeek trained a comparable model for $5.6 million, using 2,048 chips. The same level of AI capability, 1/10 of the energy cost. If the most energy-hungry approach to AI, the one that is colliding with the power grid, driving the nuclear deals, delaying the data centers, is not actually the only approach that works, then the $650 billion being spent this year is not just an infrastructure challenge. It might be a strategic miscalculation. This is the deeper story underneath the data center crisis. The companies at the frontier of AI have made a bet, an enormous, expensive, infrastructure-altering bet, that more compute equals better AI. And for several years, that bet appeared to be unambiguously correct. But the grid cannot grow as fast as the ambition. The transformers take 5 years to deliver. The grid connections take 14. The nuclear plants take longer still. And somewhere in China, an engineer trained a world-class AI model for less than $6 million on a fraction of the chips, using a fraction of the power. The question is not whether AI data centers will keep being built. They will. The question is whether the physical world, the grid, the transformers, the rivers used for cooling, the communities living next to the gas turbines running around the clock, can absorb the pace at which the digital world is trying to grow. And increasingly, the evidence suggests the answer is not at this speed, not with these methods, not without something fundamentally changing in how we think about power, efficiency, and what it actually means to build the future responsibly. This is what Unseen Drafts covers every single week. The stories underneath the stories, the physical realities behind the digital headlines. If that is your thing, subscribe now.